Hello, good afternoon, everyone here at Georgia Tech, and good morning to our distinguished speaker, Assistant Professor Stefanos Nikoladis, coming to us from Southern California, USC. And it's my pleasure to introduce our speaker today. So Stefanos is an Assistant Professor of Computer Science at the University of Southern California and leads the Interactive and Collaborative Autonomous Robotic Systems, ICAROS Lab. His research focuses on stochastic optimization approaches for learning and evaluation of human-robot interactions. Stefanos' work leads to end-to-end solutions that enable deployed robotic systems to act optimally when interacting with people in practical real-world applications. Stefanos completed his PhD at Carnegie Mellon's Robotics Institute and received his Master's of Science from MIT, actually when we were in the same lab together, Master's in Engineering from the University of Tokyo, and a Bachelor's of Science from the National Technical University of Athens in Greece. His home, if you ever happen to get to know him and get invited to his homeland in Greece, it's absolutely beautiful. Getting to see some pictures from there. His research has been recognized in the form of Best Paper Awards and nominations from the IEEE ACM International Conference on Human-Robot Interaction, HRI, the International Conference on Intelligent Robotics and Systems, and the International Symposium on Robotics. And so without further ado, I would like to turn it over to the speaker. You are welcome to ask questions in the Q&A. I will be responsible for watching them to interrupt the speaker if a good question comes up. Otherwise, we will go through all the questions at the very end. All right, Stefanos, welcome. Thanks for coming, and I look forward to your presentation.
Thank you very much, Matthew, for having me here. It's a real pleasure to be here even virtually at Georgia Tech and present this work. So let me share the screen. Okay, so today I will speak to you about our work on robust human-robot interaction, a stochastic optimization approach. And so I'm, as Matthew said, I'm an assistant professor at the University of Southern California, where I direct the Interactive and Collaborative Autonomous Robotic Systems Lab, also named for ICAROS Lab. And when I first started at USC as an assistant professor, I went to a facility for post-stroke patients. It's called the Rancho Los Amigos Rehabilitation Center. And I asked people there, if they had a lightweight assistive robotic arm, like the one that we have in the lab, what they would like the arm to do, how they would like the arm to help them. And people said things like what you would expect, right? I would like the arm to help me with eating, with feeding, with meal preparation. But especially one female patient said something that really I found very, very interesting. And that was, I would like the arm to help me comb my hair, to assist with hair combing. And so even though this is not a very basic, living activity, it's still a self-image, self-perception important issue, right? And so I thought, can we actually do something like that? Can we make a robotic system help people in a hair combing task? And so this is actually what we did. So we started implementing a system where we have a Kinect camera. The Kinect camera builds a model of a person's head, builds some mesh of the person's hair, and then what the robot is doing is it plans a path through a constrained motion to help the person on a hair combing task. So we implemented the system, we took this very nice video, we tried on different hairstyles, but then we asked ourselves, can we actually take that system and give it to that patient and tell her, we have this system for you, you can use it indefinitely. And the answer is no, right? So the answer is we are not there yet. And the reason for that is that there are a lot of edge cases. There are a lot of cases that the system may behave in an unexpected manner or may fail that are not captured by our model. And so one of these cases that you will see here, for example, is when the robot tries to move in and comb the person's hair, but it instead comes in contact with the skin. And so to account for that edge case, what we did is we used the skin conductance sensor in the brush so that as soon as it came in touch with a person's skin, the robot would stop. So, we did this for one edge case, but this is not something that, but it's not possible to cover all possible edge cases, right? Just from human intuition. And so the question then that we would like to ask is, if we are to have this kind of human-robot interaction systems interact with people for long amounts of times and in a robust manner, we need to be able to somehow identify and account for these edge cases. So one way to do that, one way to account for edge cases is through user studies. So we can have people come and interact with the robot and try to see what happens. But there are that many, even though these user studies are really essential, right? There are that many environments that we can cover through a user study. And there are also time constraints and also constraints on how many people can come and interact with the robot. So we need some kind of automatic way to be able to identify these kind of edge cases that make a system fail, but they are edge cases that are possible, that can happen, but still are not very likely, right? They are still not very common and not easily identifiable. And so can we automatically generate scenarios to better understand and test the limits of complex human-robot interaction systems? And the system that I will focus on is called the shared autonomy. So that was developed by Servin Javdani, one of my lab mates at Carnegie Mellon University, where the idea is that you have a user, and the user teleoperates the robot through, let's say, some joystick interface. And the robot uses the user's inputs to infer the user intent or the user goal. And therefore, and essentially the system uses the user's inputs as observations. So the system runs a partially observable Markov decision process to do a Bayesian update on the user's goals, and then takes an action to assist the user. So the idea is you have a list of objects in the room. The system knows where the objects are, and it has a hypothesis on which one of these objects the user wants to reach, and assists the user to reach that goal. And the motivation behind it is that if you have a robot that has many, many degrees of freedom, then it's very, very hard for the user to individually control every degree of freedom, right? It's much easier to have some system that tries to understand what the user's goal is and assist the user for that goal. And that's a system that is very, very robust. So we've used my system, the system myself, like from my studies. It has performed very, very well in a number of different environments. And so to see an example of how the system performs, so you have the two goals here, right? And then the idea is the user provides some input by moving the joystick on the left side. And the robot uses that input to infer that the left bottle here is the most likely user's goal, since the user is pointing to the left, and helps and moves the robot towards that goal. Now, and the way the studies were conducted when the work that was presented is you have some objects, side by side, and then the user provides some inputs to an interface, and the robot reaches these objects. However, what we are really interested is, can the system fail, and how will the system act if we start messing things around a little bit? So what happens if we start moving the objects on the table, or if we start adding noise in human input? So scenario generation in shared autonomy is not not a very easy, right? And the reason is that in such a system, inference of user's goal and planning are tightly coupled, right? So we cannot easily separate the inference of user's goal and the planning component and test them individually. And so this motivates a systematic testing approach. And so what we did is we said, okay, can we automatically generate scenarios in shared autonomy? And by scenarios, what we mean is, the way we define scenarios is, can we start simulating joystick inputs that a human would provide with more and more noise, like by simulating an amount of noise on the inputs? And also, can we simulate changing the object locations? So can we try, changing the environments and see how the system will behave? The scenario consists of a sequence of users' inputs provided through a joystick interface, as well as an environment setting where objects are placed on a table. And the question then becomes, can we find scenarios where the system will perform poorly, will fail? And we are especially interested in scenarios that are not very easy to find by just trying the system manually or by just knowing what the reward function is, right? So these are like rare edge cases that are not captured, that are not easily inferred by knowing how the system behaves. Now, one approach would be to just formulate this as a single objective optimization problem and try to find scenarios that minimize the system's performance. But if we do that, we will come with scenarios where the human actions will either be adversarial, so the human will, like, in purpose point to the wrong object, or completely random. Also, if we solve this as a single objective optimization problem and try to find a global optimum, what will happen is the objects will be placed very, very close to each other, because the further away the objects are, the easier it is for the system to disambiguate the user's input based on how the observation function is formed. But these scenarios are not very interesting. Like, it's very unlikely that a user will be actually adversarial when trying to work with a shared autonomy system, especially in cooperative settings. And these are also scenarios that are easy to find, like someone that knows a little bit how the system behaves and what your observation function and reward function that the robot optimizes can come out with such scenarios fairly easily. Instead, what we want to have is a diverse range of different scenarios, right, where we vary the amount of noise in human inputs, or we vary the distance of objects in the environment. So this motivates us to cast this as a quality diversity problem. So when you have a single objective, right, you try to find the global optimum. When you have a multi-objective optimization method, then you try to find a set of Pareto optimal solutions. Now, a difference between these approaches and diversity-driven methods is that the diversity-driven methods have a set of measure functions, and then they try to find, well, as the name says, a diverse range of solutions for every possible output of these measure functions. Now, quality diversity methods also have a set of measure functions and try to find a set of solutions for every possible combination, every possible output of the measure functions, but they also have a single objective that you try to optimize. So what you try to find is a set of diverse solutions with respect to the measure functions that are as high quality as possible. And so these measure functions in quality diversity are called the behavior characteristics. And it's what we want to have a diversity for. So it's what it's the functions that we want to, for every possible output, we want to generate solutions. And so what we will vary here as behavior characteristics is distance between objects. So we want scenarios where the objects are very close and very far away, and also human variation. So how much total noise do we add to human inputs? This can also be interpreted as human rationality with respect to some cost functions. So how rational, how optimal the user is. And the goal again here, the objective is to make the shared autonomy algorithm a fail. Make the shared autonomy algorithm not be able to reach the user's goal. The algorithm that we have used is a standard quality diversity algorithm. It's a gold standard is quality diversity, which is MapElits. And the way MapElits works is it assumes that the behavior space, the space specified by these measure functions, by the behavior characteristics that we want to have coverage on, is tessellated into uniformly spaced grid cells. And the goal of MapElits is to populate that space with as many cells as possible, so to fill in that space specified by the behavior characteristics, but also fill it in with as high quality solutions as possible, right? So in shared autonomy, trying to have a diverse range of scenarios that make the system fail. Now, the way MapElits works is it performs some type of simultaneous search where it builds an archive. So it first randomly samples scenarios, and it uses these scenarios to populate the archive. And then it uniformly selects scenarios from the archive and applies some perturbation. Specifically here, the vanilla MapElits applies some isotropic Gaussian noise. And does this iteratively. So MapElits has some memory of previous solutions that are successful in populating the archive. And then it randomly chooses them. It applies a variation. if new solutions fill in unexplored parts of the archive, where the archive is the space specified by the behavioral characteristics, right? The space that we want to have coverage for. If these new solutions populate the archive, then it adds them to the archive. If new solutions improve existing cells in the archive, again, it updates the archive. Otherwise, it disregards them. And so this is an iterative method. And so the result of running map-elites in the problem of scenario generation is an archive in that behavior space. So if as behavior characteristics, as functions that we want to have diversity for, right, that we want to have as many scenarios as possible, we have the distance between objects and also the variation in human inputs. That's the total amount of noise in human inputs. Then the result is a heat map where every cell here is a different scenario. And red colors indicate higher performance of the quality diversity algorithm, which, since we try to break the shared autonomy, mean worse performance of the shared autonomy algorithm. So red colors here are cases where the shared autonomy algorithm fails. And what one can do then is that we can go and inspect the heat map and inspect each of these scenarios to see why did the algorithm fail, right? So this is very, very helpful in being able to understand a complex HRI system and see how it behaves and how it works and how we can make it more robust. So we did this and we compared map-elites with random search. So random search is uniformly sampling human inputs and object locations. And CMA-ES, so CMA-ES, the Covariance Metrics Adaptation Evolution Strategy, is a single objective optimization algorithm where the goal is to find a global optimum. Now, we did some modifications to CMA-ES to allow it to explore more. But as you can see in the result here, CMA-ES focuses on one part of one region of the archive instead of trying to fill in the archive with as many solutions as possible, like map-elites. Random search also is not very successful in filling in a large part of the archive. Now, why is that? The intuition behind that, to understand that, one way to understand that is to think of the Bates distribution that you see here. So the Bates distribution represents the sum of, it's a continuous probability distribution of the mean of n uniformly distributed random variables. And as n, as the number of random variables becomes larger, then you see that the distribution becomes narrower and narrower. And so this is what we call behavior space distortion. So what happens is if you come from a high dimensional search space, in this case here the n random variables, to a lower dimensional behavior space, which in this case is the one dimensional space where in this case it's a mean of the variables, then what happens is even though you uniformly sample the high dimensional space, the probability mass gets concentrated on a very small region. And the same again happens in our behavior space here. And the intuition behind that is the following. Let's say that you want to compute the distance between multiple objects. Now you can uniformly sample objects on the table, but when it comes to, let's say, their mean distance or the distance to the center of the table, the chance that you would through uniform sampling end up with objects that are on the edges of the table is very, very small. And at the same time, the chance that the probability that all objects would be sampled in the center of the table is also very, very small. So even though the objects are uniformly sampled on the table, the probability mass of the distance that gets concentrated on a very, very small region. So this is why when it comes to, if the goal is to fill in an archive, a lower dimensional space, random search tends not to perform very well. On the other hand, what map-elites does is it does some form of simultaneous search, where it builds an archive of previously found good solutions and perturbs the solutions, and that's much more efficient. And so we did compare map-elites with random search and CMA-ES, and as expected, we found a significant difference in performance. We measure performance using the quality diversity score, which is a metric that that captures both the coverage of the archive and quality of solutions. So it's the sum of performance of all cells in the archive. It's a metric, it's a quality diversity metric that shows both how diverse the archive is and how good the solutions returned are. Now, what we can do then is we can go to the archive generated with MapElites and inspect and see, has the algorithm, has a shared autonomy algorithm, the algorithm that we want to test, failed? And if it has, then why did it fail? So this is how we would expect the shared autonomy algorithm to perform if the user is optimal and if the objects are nicely placed next to each other. This is the archive returned by MapElites, and so can then inspect the cells in red color. These are cells of high performance. These are cells where the shared autonomy algorithm has failed, and see why did this happen. So for example, we can pick this cell here, and this cell has high variation, which means that there is a lot of noise in human input. And it has red color, which means that the shared autonomy algorithm timed out without reaching the actual goal. And we see how this looks like if we reproduce it in the real world. So what happens is there is a noise in human input, and the shared autonomy algorithm, which uses a distance-based metric, incorrectly infers that the goal is the right bottle and goes to that bottle, even though the user's goal is the left bottle. And at the same time, we observe that it gets stuck there. So the reason for that, we actually did a little bit of investigation on the algorithm. And the reason for that is that it uses some non-constant reward function that tends to be much, much lower when the robot approaches the goal. Now, okay, that's a case that one would expect, right? If the human input is very noisy, then the robot will incorrectly think that the actual goal is not the true user's goal and go there. But what we found very, very interesting is that there were several failure cases, even when human variation is very low. This means even if the user is almost optimal, the robot would still sometimes fail. And so if we again reproduce this scenario, we see that the object positions found by the scenario generation algorithm were so that the disruptor, the, let's say, wrong object, would be placed right in front of the user's goal. And so what happens is the following. In the shared autonomy algorithm, the observation function is a distance-based function. And here, even though the user is pointing towards their desired goal, the robot incorrectly thinks that the user wants to go to the nearest goal, which is the white bottle, goes there and gets stuck there, even though the user is nearly optimal based on the cost function assumed by the algorithm. So that was an interesting edge case because it was something that we did not know in advance. So when we tried testing the system, we did not know that this is something that the system can fail. And it was also not very intuitive in the beginning, but it was an edge case automatically found by the scenario generation. So to summarize the contribution from this part of the talk, quality diversity algorithm MapElites outperforms random search and as well as state-of-the-art single objective optimization methods, highlighting its promise for automatic evaluation of algorithms in shared autonomy. Now, a limitation on that is that MapElites still requires a large number of evaluations to achieve good results. So MapElites is still an expensive algorithm that requires having a population of solutions and then iteratively perturbing that population. So can we do better? Can we actually improve the efficiency of MapElites? And so the way MapElites works, as we said in the first part of the talk, is, it forms an initial population with some sort of random search. It populates the archive, and then uniformly selects individuals from the archive, applies some perturbation, and does this iteratively. Now, can we still leverage the archiving properties of MapElites while doing a little better in terms of adaptation, in terms of how we pick solutions and how we move through this behavior space? If we look at how CMA-ES, the state-of-the-art single objective optimization algorithm that we compared against in the first part works, is, well, CMA-ES models a distribution of the population of solutions as a multivariate Gaussian. And the way it works is it selects the best solutions and ranks them based on fitness, based on that single objective that it optimizes. And then it uses that ranking to update the mean and the covariance metrics of the multivariate Gaussian. And it also maintains a history of aggregated changes named evolution path, similarly to momentum in stochastic gradient descent. So CMA-ES has achieved really state-of-the-art performance in many optimization benchmarks. It has been used a lot for falsification of cyber-physical systems. It's a very powerful algorithm. So what we thought of is, can we actually combine the adaptation properties of CMA-ES with the archiving properties of map-elites to develop a new algorithm? And the algorithm that we came up with is called Covariance Matrix Adaptation Map-elites, also named CMA-ME. Now, the way CMA-ME works, and as I will explain in the next slides, is it has a population of CMA-ES instances. We call these emitters. And each emitter, so first it has a scheduling. It has a high-level scheduler that selects which emitter should generate a solution at every point in time. So it does this in a round-robin manner. And each emitter is like a CMA-ES instance. It maintains a multivariate normal distribution. So it maintains a mean and covariance matrix and also an evolution path. However, instead of each emitter trying to optimize a single objective, the emitter updates its mean and covariance metrics based on interacting with the archive. So we proposed the different types of emitters, different types of CMA-ES instances, an optimizing emitter, and random direction emitter, and an improvement emitter. So I'll focus on this talk on improvement emitters because we actually found that they can perform very well in the domains that we are interested in. And the way improvement emitters work is they have, as a CMA-ES instance, an improvement emitter has a mean and a covariance matrix. But instead of ranking solutions based on the single objective, it ranks first solutions that discover new cells. And then it ranks solutions that improve existing cells. And so essentially it estimates, the assumption here is that if you have increasing steps in the search space, and these tend to improve the archive, then the improvement emitter doubles down on that direction, right? So if there is a direction in the search space that improves the archive, then moving further in that direction is likely to improve the archive further. And so by doing that, the improvement emitter the intuition is that it prioritizes improvement of the archive, and especially prioritizes exploration of the archive by ranking first solutions that discover new cells and then solutions that improve existing cells, and uses that ranking to update the covariance metrics on search. So we have actually implemented this and compared it with map-elites against different benchmarks, and we found a very good performance of CMA-ME. And then we thought, okay, what's the hardest domain that we can test this new algorithm CMA-ME? And so we picked the game Hearthstone. So I have never played the game myself, but my understanding is that in Hearthstone you have a bunch of cards, and you place them on. You have a deck of cards, and you place them on the board. And then the opponent also has some cards that you cannot observe, so it's a partial information game, and puts their cards on the board, and then the goal is to reduce the opponent's health to 0. And so I'm not sure. I'm still not sure if that's the hardest game problem that we could find, but it's still a 2-player stochastic adversarial game with partial information. It's also very interesting because, well, first, each turn that you take is not one action; it's a sequence of actions. And also, as a Hearthstone as a domain is very interesting because it suggests a mental learning problem where first you need to be able to choose good decks. So there are a number of possible decks, and then you have to reason over which deck the opponent is choosing and then choose a deck, and then also learn how to play that deck. So it's like learning how to play chess, where you also have to pick the pieces on the board. Now, in this work here, we assume a fixed deck. So we only reason about how to use the CMA-ME to learn good strategies to play Hearthstone. And now how we represent a strategy, we can represent it as a neural network that ranks board states. And then we can use CMA-ME to optimize the neural network parameters. So the idea is you have a neural network, and then the neural network learns or approximates a value function, essentially, and then we can use this ranking to pick to select the actions for a turn. And the objective is to win as many games as possible. Now, the behavior characteristics, the measure functions that we want to have diversity for, is average hand size and number of turns. So this is interesting because this essentially means that we want to have a diverse range of different strategies that are high quality, that win the game against a fixed suit of opponents. But we also want to vary the number of turns. So we want to find strategies that are very, very aggressive, and also strategies that are more conservative and rely on optimizing and long-term reward rather than greedily trying to win the game as fast as possible. And so you can see here how CMA-ME performs compared to map elites. So this is a behavior space, and lighter colors mean a higher quality of solution. So, and you see that CMA-ME actually discovers a much larger portion of the archive, and also the quality of solutions is much, much higher. And so we compare the CMA-ME against a bunch of baselines, CMA-ES, map elites, and map elites line is a recent variation of map elites, where instead of, when perturbing the solutions, instead of using an isotropic variation, we use non-isotropic variation, and we see that the results were quite unreal. So there were CMA-ME performed orders of magnitude better in terms of the quality and diversity of solution. Or if not orders of magnitude, it had about twice the quality diversity score. And so what was actually also very, very interesting is that if we look at the distribution of solutions, we see that CMA-ME had a large number of solutions that had a very high winning rate, much, much higher winning rate than the baselines, even much, much higher winning rate than CMA-ES, where the CMA-ES, the single objective of CMA-ES was to find solutions that maximize win rate. And so the reason this happened when we investigated how the algorithm performed is the following. So first, CMA-ME found solutions that win the game very quickly, so aggressive solutions. But then there was not much that one could do with these solutions, right? These solutions achieved some win rate, but they were limited. And then because we have a behavior space where we have the average number of turns, CMA-ME started exploring that behavior space and trying to fill in that space with solutions that last much longer. And then started improving upon these solutions, and these were the solutions that achieved the very high win rate that we observed. And so it's like playing chess, where you can easily learn how to win a game by, let's say, fool's mate, right, in 4 moves. But then eventually you can get that far with that strategy, right? And then what you eventually want to do is start to learn how to play longer games, and eventually build on these longer games and improve on these games, and then that's how you become, you learn successful strategy. And so in a sense, because of the way the behavior space was structured, CMA-ME provided the natural curriculum for learning. And this is something that we are excited to investigate further in the future. And so the contribution from this part of the talk is that CMA-ME performs state-of-the-art quality diversity algorithms by combining the adaptation properties of CMA-ES with the archiving and mapping properties of map elites. Now, the next question that would be interesting to ask is, can we leverage CMA-ME to procedurally generate even more complex content? So we have a powerful algorithm, and this algorithm can generate a diverse range of high-quality solutions. But can we actually leverage this algorithm to solve problems where the content can be very, very complex? And so one interesting problem is procedural content generation, and especially generation of video game levels. And so if we want to generate, video game levels that look like human-authored examples, we can use deep generative models like generative adversarial networks, and this can have actually been shown to produce very, very realistic content. However, there are two issues. So the first issue is that GANs, generative adversarial networks, are quite hard to control. So it's hard to tailor a GAN towards generated content that has very specific properties that you may want. The second issue, and that's something that I learned when I worked at Square Enix, the side note is that before actually even coming to the States and starting graduate school, I worked at a video game company in Japan, and I worked on procedural content generation. And what I learned from there is that designers very rarely know exactly what they want. So what they want is they want to have some automatically generated content that is diverse with respect to specific attributes that they can then inspect and choose from. And so the question then is, can we use GANs to generate a diverse and high quality content, and while at the same time retaining stylistic similarity to human-authored examples? And so what we did is we used CMA-ME to perform what we call latent space illumination. So what this means is that now we are the search space, like it's solution that we generate is a latent vector, and then we pass the latent vector to a trained generator, and then we explore the latent space, right? So we generate latent vectors in order to generate solutions, to make the generator output solutions, output levels that are high quality, they are playable, right? And they are also diverse with respect to specific metrics. And we call this latent space illumination. And so this is what we did. So we actually used we had the human-authored examples, and we used those to train a GAN, to train a generative adversarial network. And so that's how we can generate a level. And then we used CMA-ME, where the goal is to explore the latent space of a GAN, like the input that we provide to the generator, so that it fills in the behavior space with as many solutions as possible and as high quality solutions as possible. So quality here is assessed by playability. So we used an AI agent to play the level, and then high quality level was a level where the AI agent was able to complete the level fully. And the behavior characteristics, what we want to have diversity on, was the number of enemies. So we want levels with a lot of enemies or very few enemies, and also the number of sky tiles. So from 0, let's say, to 150. So sky tiles are tiles that are very, very high in the level. So for example here, right? So here you can see a level with a lot of enemies and a small number of sky tiles. Here, on the other hand, you can see a level with no sky tiles, right? So it's like only ground tiles, so no tiles very high up, and a large number of enemies. And this is a level with a large number of sky tiles and no enemies. And also you can have a mixture of the two, right? So you can have levels with tiles and also sky tiles and enemies. And all this was generated content, right? With by doing latent space illumination. And again, we compared CMA-ME against MapElites and MapElites line, the variant of MapElites, and also random search. So random search is directly sampling the GAN instead of doing quality diversity search on the latent space, and CMA-ES again on the latent space. And we see that, we didn't see the huge difference that we saw in the Hearthstone domain, but we still saw a significant improvement with CMA-ME. Now, another thing that a designer may want is they may want to not specify specific attributes like number of enemies or number of tiles in the sky, but instead provide some ground truth scenes, like, for example, have some human-authored scenes, and then use these scenes as a way to generate levels that are more or less similar to each of the two scenes. And so we can actually assess similarity of a level using the KL-Divergence metric, the KL-Divergence between the tile distribution of the Groundtruth scene and the output scene. And so here KL-Divergence in the x-axis means higher values of KL-Divergence means smaller similarity to the first Groundtruth scene. And similarly, the y-axis, higher values means smaller similarity to the second Groundtruth scene. So for example, here in the behavior space, so that's the output of CMA-ME with these behavior characteristics, we can see that this level here is very similar to the second Groundtruth scene and not similar to the first one, right, because of the KL-Divergence values. This level here, on the other hand, is the opposite, so it should be very similar to the first scene. And what is interesting is this level here, where we try to maximize dissimilarity, so minimize similarity to both scenes. And what latent space illumination did is it found levels with tiles that did not exist in any of the two scenes. So that was the way of the algorithm to find levels that maximize dissimilarity. So you see this weird square tiles, right? This did not exist in any of the two Groundtruth scenes. And you see that all levels generated are very, very high quality, right? So all are playable by the A-star agent. And again, we saw an improvement in performance when using CMA-ME compared to the baselines. And you can see also qualitatively how the archives look like. So you can see that CMA-ME has a much larger and richer archive, and also compared to map-elites, and also compared to CMA-ES. Now, we also want to assess whether these similarity metrics that we use to position levels on the archive actually correspond to perceived similarity by users. So we did a user study where we selected randomly levels from the archive, and then we asked users to rate the levels, rate the similarity of the levels to each of the two Groundtruth scenes. And we used the ratings to position the levels in space. And so in a sense, this says that, if we position the levels on an imaginary archive where the coordinates would be based on how users rate similarity, not on the objective metric of similarity, the KL-Divergence, how would the levels be placed? And so different colors here represent different levels. And you see that, of course, there is a difference, right, in scale, but overall, you see that there is a strong similarity between the two plots. And what we found is that actual how we position levels in the archive matched to some degree how similar or dissimilar people perceive the levels to the Groundtruth scenes. Okay, so this work was led by Matthew Fontaine, PhD student in the Icarus lab. And so there are many applications where we wish to have not a single optimum, but have a diverse range of high quality solutions. And one of them is scenario generation for human-robot interaction. So we saw how quality diversity can help and have good performance in generating scenarios in shared autonomy. I presented a new algorithm for improving the quality and diversity of solutions found. And we saw how this algorithm performs well in several game domains. And we show also applications in procedural content generation. We also have some work under review that shows how CMA-ME, this new algorithm that we presented, is also very effective in generating scenarios in shared autonomy. Now, if you are interested in learning more about quality diversity, we also have open sourced quality diversity library, and we have several tutorials. So some tutorials are based on a lunar lander. So here we use CMA-ME to explore different strategies on how to land lunar lander. And so if you want to also learn how to land the lunar lander like a space shuttle, please take a look at the PyRibs library, which is where we have the tutorials. And we also used one of the tutorials shows how you can use CMA-ME to do latent space illuminations to generate fake digits. So these are, so here we do latent space illumination on a trained GAN where the goal is to generate digits. So all these digits are classified as 8. but with the behavior space is the lightness and boldness of digits, so we can also generate a diverse range of fake content. And this was this library was the development of this library was led by Brian Tianaka. Now, for the remaining part of this talk, I would like to also speak and give a brief overview about other work that we have done in the lab and work related to learning human preferences. So that's a work that I started in my graduate studies at MIT. This is Matthew here, by the way, in the Interactive Robotics group. And so one of the work that we have done was how to efficiently learn human preference. And so the insight that we had at that time was that if we have people and people provide demonstrations on how to do the task, then we can, people will tend to cluster into a few dominant types. And therefore, if we learn what these types are, this can provide a strong prior so that when a robot sees a new user, the robot can quickly infer the type of the new user and adapt to that user. However, when we tried actually implementing this on a more complex task, specifically a bookcase assembly task, this did not work well. And the reason is that what we found out is that users, even though they do have dominant preferences, their preferences exist in multiple resolutions. So people here have a preference on whether they should assemble the boards first, like the participant in the video, or the shelves first. But then they may also have a lower level preference on what would be the sequence of the cells to be assembled. And this is not something that we captured in the past. So what Hiram Nemlekar, a PhD student in the lab, came up with was we can actually learn preference in different resolutions. So first we can learn a preference over event sequences, over high-level features. That was inspired by work on clickstream analysis, and then cluster people based on these high-level preferences, and then perform the second round of clustering in a hierarchical manner to further cluster people on their lower-level preferences. And so the effect of that is that then if you have this kind of tree, right, or this hierarchical clustering saved in memory, then when a new user comes, you can very, very quickly infer how the user wants to do the task. And therefore, the robot can predict their next action and effectively support them for the task. We are now extending this to a model airplane assembly task, which is a much more complex task. And the students that work on model airplane assembly purely focus on the assembly on airplanes and will never go out and fly the airplanes for fun, wink, wink. And this work was, we were happy that this work was has been funded and supported by the NSF National Robotics Initiative, and this is a project that started this year. Now, if you have worked with humans, you also know that human demonstrations tend to be not always optimal. And actually, some of the demonstrations that people provide can be blatantly wrong. So what Anirudh Puranik came up with was an algorithm to be able to learn from suboptimal demonstrations by using signal temporal logic. And that was work presented at Corel 2020. We also looked at how can a robot interact and collaborate with multiple users. So you can imagine a robot in a healthcare facility interacting with different patients, or a robot in a factory line interacting with different workers. For example, the robot having a tool and the robot needing to design which workers should receive a tool. And so one way to model this interaction is to assume that there is some reward associated with interacting with a specific user, for example, based on how skilled the user is. And then this becomes an exploration and exploitation problem where we want to infer the reward of interacting with a given user, but also maximize the long-term expected rewards, which would be time to completion. And so we can cast this as a multi-arm bandit problem, right, where the robot tries to infer what the rewards are, but also maximize the expected reward. But if we do that, then what we have observed is that the robot would just pick the most skilled worker and give all the resources to them, one after the other, because that would be the optimal solution to do. However, in practice, we found out that if that happens, then the overall performance will tend to drop. And the reason is that other workers will tend to become disengaged and also lose their trust in the system. And so instead, we proposed a fair resource allocation algorithm where we impose a minimum allocation rate to all workers. So we call this a fairness constraint. And we found out that if we do that, and we provide also some theoretical guarantees on performance, then this helps improve team performance and overall trust in the system. And we further extending this work to account for context. So if a worker is better in one context, like drilling, and the other is in screwing, let's say in an assembly task, then accounting for context based on the current task step further improve performance. And this is a work that was presented in the Conference on Uncertainty in Artificial Intelligence. So as I move towards the end of the talk, I would like to come back to the original problem of care combing. So I still haven't forgotten about that, and we have actually been building more and more on that. So we actually had a demonstration, a live demonstration of the system at NeurIPS 2019, where Nathan here is sitting, and the robot in real time builds a model of his hair and his head and hair, and then helps him comb the hair. And you can contrast the motion of the robot for Nathan compared to Yura. So Yura was an undergraduate student funded through the NSF REU Opportunities Program, and she led a lot of the development of this system, where you can see that she has longer hair, right? So then the robot will do a much longer motion to be able to comb her whole hair. So we are still not at a level where we can give the system to the patient that asked for it and tell her, you can use it indefinitely. But we are making steps in that direction. Now the problem with hair combing is that if something goes wrong, right? If there is an edge case that you haven't accounted for, then the robot will pull your hair. But with the roof bolter here in mining operations, this roof bolter will actually cut your arm off. So we also extended this work on scenario generation in roof bolting, in robot assisting roof bolting. And so the idea is how we can have a human-robot collaboration paradigm where a robotic assistant helps making the operation less dangerous in a roof bolting operation. And so this is a work, and that's an ongoing work that is in collaboration with the University of Kentucky, and it was funded by the Alpha Foundation. Finally, I would like to mention a little bit of work that we have done in teaching. So one of the things that I have always wanted to do is build a class that is based on axial hardware and helps people learn robotics by working on axial robots. So we actually, with support from the department, we got 5 robotic arms, and we have split students to labs where each student in a small group works on a robotic arm, and works on building the entire pipeline on the entire manipulation and planning pipeline on a JCO robotic arm. Now, this year, this was all done in simulation, but we are hopeful that from next fall, the lab will be back in person. Okay, and of course, all this work was done by the students in the interactive and collaborative autonomous robotics group at the University of Southern California. And with that, I would be happy to take any questions.
All right, well, thank you very much, Stefanos, for that presentation. For everyone in the audience, if you could please type on the chat or the Q&A, please go to the Q&A tab on the right that you can list your questions. And while we're waiting for those, I'll go ahead and kick us off. So Stefanos, it was funny to see that old picture of us in the lab together. And I liked how you talked about some of your work back in 2015 and kind of inferring user preferences, and how you went from that to reason about how user preferences are kind of at different levels of granularity. where do you think the field is going in modeling user preferences for robotics? Do you think that we've kind of solved the problem, or do you think there's something that eludes us?
Yeah, no, I think this is a great question. I think, so I think there has been a lot of work on user modeling, right? So what is the right way to model the human user? Is it to assume that the user is optimal? Is it to have a bounded rational model, or a model of human bounded rationality? Is it to assume that user preferences are correlated? And there's definitely very exciting work on that front. I think one important aspect that might be underrepresented in ongoing work is environments, right? So people's preference depends definitely on their cost function and their reward function and on priors, and that's something that, as you know, we have been looking on, and I know that your lab has actually been doing really great work on that. But I think, also an important aspect, maybe orthogonal to that, is how do environments affect different preferences? How do object locations and object settings affect preferences? And how can a robot account for this context in the decision making? And so what I'm very, very excited about, and I think what we are trying to show with the work on learning edge cases, is distilling that and finding and showing that when reasoning about systems that help people in assistive tasks, we should reason not just about distributions of actions, but also distributions of object locations, of obstacles in the world. And so I think for me, that's a very promising future direction. Yeah.
Great. Thank you, Stefanos. And I guess to follow up on that, what do you think users actually want? So this is a question that I struggle with. Do you think users want robots to learn and infer what their preferences are? Or do you think people just want the ability to just tell the robot, here's my preference using some kind of interface, and just be done with it? I think that's kind of a debate we have. Is machine learning and inference the right approach, or is it just, is it the right UI and user control?
Right. I think the best way to think of that is to see how people interact with systems right now, with autonomous systems right now. So, when I'm driving, I'm happy to put the address on the GPS and have the GPS tell me how I want to go. But there are times when this can get pretty annoying. So there are times where I just hope that the GPS stops telling me to go left when it's clearly that I want to keep going straight. And so I think there is a phase where users want to clearly specify preferences on the system, but there is also a phase where, as users become more and more accustomed with using these systems for long periods of time, there is an expectation that systems would be able to, and robots would be able to learn and develop expectations on users' behavior and adapt to these expectations. I think that would make the interaction much more satisfying. However, there is a thin balance, like I think what your question implies, right? So there is a balance where too much autonomy can hurt, and we show this a lot in shared autonomy. So a very similar question that I get asked is, why shared autonomy? Why not just have the robot autonomously pick up a cup? And that's not what users want. Users, especially users that have some form of limited mobility, they really want to have something that they can control, and they can control like the trajectory, they can control the motion, they can control their goal. And so that's something that that's a thin balance that is it's not an easy problem to solve. Yeah. Oh, Matthew, I cannot hear you.
I'm muted. Sorry about that. Yeah, no, thank you. I got that question from Bilge Mutlu when I was giving a seminar, and I think that's just like an important critique for HRI researchers as I think that we need work kind of identifying that. But I agree with you. I think it's going to be a mixture. And I like the autonomous driving example. You don't want a car to try to infer where you want to go. That would be very annoying. Exactly. But there's a lot of other environments where that is really useful. I wondered for the hair combing example that you gave us at the very beginning, do you see that being applied to like sponge bathing or other types of rehabilitation work where a robot is actively engaged in manipulating a patient?
Can you repeat, apply to which application?
Oh, like more assistive tasks, like sponge baths. Like Charlie Kemp at Georgia Tech has some works with like sponge bathing, with looking at conductance and kind of pressure, and it'd be interesting, like what other tasks could stuff like that be used for?
Right. So I think that there is definitely an opportunity for a large number of tasks, and building a model of. I mean, the work that we do now on hair combing is more focused on inferring a person's hairstyle. So building a model of a person's head and building a mesh of the hair and planning a path through the hair. And that's slightly different in that than other assistive tasks like grooming or dressing or like sponge bathing, because then it becomes less in the emphasis is placed less on how much pressure you should apply and how to track the human body, and more on the actual hairstyle, right? So people have specific preferences on how they would like the hair to become.
Yeah.
Whereas in sponging, I would imagine that you would want coverage, right? So you want to sponge, don't want to leave parts of the body that are unsponged or unbathed, right? So I think there is definitely a difference there. At the same time, though, I can imagine that in the same way that you want to learn individualized preferences on hair combing, there are individualized preferences also on bathing, and the system should account for that. So I think there is a promise for a general framework that accounts for this type of preferences. Yeah.
Cool. Well, I think we have time for one final question. I got one here. You mentioned that CMA-ES performed very well at finding a diverse set of strategies. Do you think CMA-ES could instead produce strategies that the human would find fun, similar to some of the goals behind procedural content generation?
Great. Yeah, I think the question maybe implies CMA-ME, which is the algorithm, the new algorithm. So CMA-ES, I want to clarify that CMA-ES is like this single objective optimization method, and then Mappelitz is a quality diversity method, and CMA-ME combines the adaptation properties of CMA-ES with Mappelitz, right? So, I mean, CMA-ES can also find some range of diverse strategies, but I think if you want to have a diversity, then quality diversity algorithms like CMA-ME tend to perform much, much better. Now, to answer the second part of the question, definitely. So what we would need then, that's not so easy though. So the way we estimated quality, for example, in video game levels, is by having an A-star agent play the level and see how far it went, right? Whether it finished the level or not. We would need some objective metric of quality for fun, and that's less straightforward. So if we can associate fun with some behavior characteristics, right? So if we can say that, having a given number of enemies or having a given number of features, this is correlated with a level being more fun. Or if there has been a lot of work, so for example, work done by Seth Cooper and Northeastern on what's the right difficulty level, right, for a level to be fun. Maybe a difficulty level people have used, can the user complete the level 60% of the time? So if we can, tailor the quality, this objective metric that we try to optimize while still retaining diversity, so that it is closer to a target difficulty level instead of just wanting the level to be, let's say, feasible or valid, then I think that's definitely something that could be possible. And I think that's a very interesting direction.
Cool. Well, thank you very much, Stefanos, and thank you to our audience for attending today. If you want to talk to Stefanos, please follow up with him, or if you need to get in contact with him, you can reach out to me. we'll look forward to seeing you all at the next IRM seminar. All right, thank you, Stefanos.
Thank you very much for having me. It's a real pleasure.